So yesterday's lecture, I did like a recall of what was done in the two previous lectures, which was about mixing. Okay. Again, this is a statistical property that goes, in the same logic that we were studying. We want to study invariant measures, ergodic measures. We add more structure. We want mixing. Okay. Mixing, we have seen, I recalled yesterday that mixing is a statistical property that is stronger than ergodicity. And we have different type of mixing. We have topological mixing. We have mixing like measure theoretic mixing, and we have also weak mixing. Okay. So today's lecture is about equivalent systems. Okay. So today we'll do chapter 8. Which is about equivalent system. So, in general, in dynamical system, usually you have your system that you want to study, but maybe the system is complicated, it's difficult to study, but there's another system that looks like the one you want to study, but you want to study an easier system and get the informations from this type of equivalence. So in this chapter we want to define what it means for two systems to be equivalent, and with this equivalence, what are the properties that goes through this kind of bridge of equivalence. So what are the properties that you get? Okay, so there are different types of equivalence. So in the first thing we will see ergodic equivalence. So in this chapter, usually we will suppose that we have two dynamical systems. So we suppose that we have two measured space. So mu and B. So this is Bm. Okay, this is a sigma algebra, and nu. These are two measured spaces. Okay, we have these two measures. So this is a topological space. This is a Borel sigma algebra. This is a measure, a probability measure. Okay, these are probability measures. Okay. And we suppose that we have two dynamical systems, F on M and G on N. Okay. We suppose that mu is F invariant, and nu is G invariant. Okay. So yeah. Okay, so definition. So we say that these two dynamical systems, F mu and F nu, are ergodically equivalent. Yes, thanks. Yes. Thank you. We say that these two are ergodically equivalent if you have measurable subsets X of M and Y N. These are full measured subset because so mu of X is 1. Nu of Y is 1. Sorry, I said 1 and I read 0. And a bijection, a measurable, if we have this, and a measurable bijection. C from x to y with measurable inverse, okay, with measurable inverse such that we have these properties phi star mu equals nu and nu phi conjugate the two dynamics. This G composes here. So think of having your two spaces. You have M here, you have mu, and you have F that is acting here, and you have N and nu, and you have G that is acting here, and you have C that is doing this, and nu is phi star. Yeah. Okay. Yeah. Yeah, it is called, this is ergodic equivalent. So, I mean, it's easy to see that this is an equivalence relationship, okay? So, remark that this defines an equivalence relationship, this property. So, let's see examples of this type. I think I kind of sketched this sometimes back, like a month ago. So if you have this dynamics, the decimal expansion, f of x equals 10x mod 1. So this is just like this, where you have 10 branches, okay, 10, okay. Okay. You have 0, 1 over 10, 2 over 1 over 5, and 9 over 10, and 1 here. So, if you represent the a number on 0, 1 by its decimal expansion, so writing x in 0, 1 as x equals 0.A0, A1, A2, and so on. This is a decimal expansion. You see that this dynamics is only, when you apply to this, it's just shifting to the left, okay, shifting this sequence to the left. So f can be seen as just shifting to the left. And this is a motivation of, of defining a map on the symbolic space 0, 1, 9 to the power n to 0, 1. It takes a sequence an and gives phi of an of this sequence an is the sum. After I will give a general version of how to do this n plus 1, which is just, if you see, this is 0 points a0, a1, a2, and so on. Phi is definitely surjective because any guy you take here, it has a decimal expansion, but phi is not injective. Well, because you can have this 0.1, everything else is 0, and this guy 0.0999, and so on. These two, they will have the same image by phi, so phi is not injective. That's the the good thing about this is you don't want this bijection to be on the whole space. You just want it on a space of full measure. Okay, so this observe that the points with same image, they correspond to sequences with which is finite here. The decimal expansion is finite here. Okay, with same image corresponds to was sequences that all digits are the same except finitely many of them. So that all digits are the same except finitely many of them. Okay, and this number of points, as you can see, is countable. You can see it just corresponds to, if you look at it in this side, it just corresponds to the rational numbers. Okay. So you define this subset of this space where you throw away this point that prevent this map to be injective. You define X. This number of points with infinite number of digits different from 0. Digits different from 0. Okay. And you define the corresponding guy here, Y, the subset of 0, 1. So this corresponds to the points whose decimal expansion is infinite. Okay, these are the reals whose decimal expansion are infinite. Okay. Yeah, so with this you can see that phi restricted to X. Phi as a function from X to Y is bijective. And phi is, is measurable by construction, by this definition here. It is measurable. And to see that phi minus is also measurable, you just need to see that the image, so observe that phi of X, the image of X intersect. We have seen this, the cylinders, the topology, the way we define it here, we have seen it this, if you take this cylinder A0, A1, A m minus 1, so this defines the topology here on this space. M minus 1 is so X intersect with this guy. Yes, this is what I wanted. Is the intersection of Y with an interval of length 10 to the minus m. Okay, mod 1, 10x, yeah, of Y with an interval of length 10 to the minus m. Okay, yeah, with this you can see that if you take nu is a Bernoulli measure here, we have defined it in the previous lecture. Nu is Bernoulli in this. Okay, when you restrict it to X, you use the same observation to see that phi star nu is m, which is the Lebesgue measure. Okay, Lebesgue on the interval. I mean, it's clear that this guy, this conjugate the two dynamics. So, sorry, I didn't define the other dynamics. The other dynamic is the shift map. Okay, on X, you have the shift map. Okay, we have seen this before. So, if you take sigma, this is a shift map. You can see that sigma compose phi composed with sigma equals f composed with phi. Okay, that's just easy. So it just tells you that these two systems are. But this is general. This is what I sketch here. It belongs to a more general scheme. Like for any full branch map, you can do the same thing. Let me just do it. Tell you how it works for general full branch map. Okay. So remember, if you have a dynamical system on the interval, so this is 0, 1, you have a partition. Let's say I use here finite partition. Okay. Partition of I1, Ik. So F full branch, so an expanding. Yeah, you want this to be expanding. That's important. So F expanding uniformly, okay, and full branch. So the definition of full branch, if you remember, it comes with a partition. So it encode this f of I is a whole interval. Okay. Okay. Now, if you have this, you can always find an equivalent system with a symbolic. Yeah. So how to do this? You do like this. So you want to find this map C. I like to define it like this. So you want to find what I will define will be C minus 1 from I to a certain symbolic space. This is something I would define. Let's say some 0, 1, k minus 1 to the power n. How to define this? So you define it such that C of x. So this is a sequence. So I use k here. K has to do with the number of branches you have. The number of symbols will be the number of branches you have, okay? This is a sequence. Now the nth component of the sequence is an, which is among this guy, is such that f n of x is in I n, is in I a n. Okay, you just track it. You just look. I take a point. I want to define the sequence that corresponds. So if the point is here, the first digit is 0. Okay, I want to know the second digit. So I will look at the image of this point. So this point is mapped somewhere here. I look at which partition element it belongs. So that partition element will define the digit that you would have. Okay, like this. Is it kind of okay, clear? Yeah. So I think I explained this sometimes in the past. So this a n is in this set, is the symbol. So you use 0, 1, you could use anything else. Yeah, you could use anything you want. So these are just symbols, okay? Now you might ask whether this map is well defined, okay, because you have partitions, their boundaries, you don't know where they belong, so you have to take out the boundaries. So basically you would define your space X as a subset of I, and X will be X minus, okay, I minus the pre-images of the boundary of these intervals, the union of f minus n and then 1 of, okay, so I have two unions here. So union on j here of f minus n I j. J goes from 0 to k minus, okay, to 1 to k, okay, 1 to k. So basically you just take out the boundaries and their pre-images, okay, to make this map well defined, because this doesn't make sense if this point is in the boundary of the element. So I should write here interior, sorry. Okay. And this set is countable. Oh, I'm sorry. Yeah, I'm sorry. I'm very slow today. So this is a boundary. I'm sorry. You forgive me. So this is the boundary of the partition element. Okay. This is a boundary of the partition element. Yes. So you take out this, and this will be a bijection to its image. So you define C from X to C of X. Is a bijection. This will be a bijection, and it will satisfy these properties. Okay, if you can define the Bernoulli measure here, and you can see that, yeah. So this, I won't be able to do it fully because we don't know what the invariant measure will be for this dynamical system. Okay. But for this dynamical system, we should know at least theoretically how to find the invariant measure for this dynamical system, because you can define the transfer operator and and find the absolutely continuous invariant measure. Okay, the measure that is absolutely continuous with respect to the Lebesgue invariant, you can find it. Okay, so there is this fact that Actually, already this is a topic of presentation, that F has a unique measure mu that is has a unique measure that is F invariant in I'm slow. I should be more careful about what I'm writing here. Sorry. Okay. So F has a unique invariant measure that is absolutely continuous with respect to the back. Unique invariant measure mu that is absolutely continuous with respect to the back. You know, one could if one wants to do a presentation like to prove this already is something non-trivial, and then that, you know, if you take nu, the Bernoulli measure here, phi star nu equals mu, and nu conjugates the two dynamics, the shift map here, psi conjugate the two dynamics. So I want to write psi composed with sigma composed with F. No, this will be psi and this will be F. Okay, yeah, this is something very interesting to know how to do it. Okay, for full branch expanding maps, how to prove that you have a unique measure that is absolutely continuous with respect to Lebesgue, and also to do this correspondence. I think I'm wasting too much time on this. There is another interesting exercise on this. So if you see, what I have been doing there is you have your dynamical system M, F, and you have the symbolic dynamics here, sigma, and you have the conjugation that do this commutation. Okay. So this is a shift. Usually this is easier to study. Okay, it's easier to study in a sense that I mean, it depends on what you want. Like, you can find easily the periodic points here, the dense orbit here, and many other properties. And all those properties, they just go through this correspondence easily. You can just lift them to this dynamics easily. And yeah, but there are something you don't get, which is like differentiability, because this space doesn't have a differentiable structure. It's just a topological space. Like, if you're interested in knowing something about, you know, eigenvalues or at fixed point or at periodic points, this doesn't give it, because this doesn't have a smooth structure. Now, another interesting question you might have is when you have another symbolic dynamics here, when are these two equivalents? Like, you have two symbolic spaces, so when do we have this? When do we have this diagram commits? Because as I said, you can just see for this type of dynamics, you can because so when you take, for instance, this map 10x mod 1, like you take 10x mod 1, oh, let's just take 2x mod 1 to be simple. Okay, to be simple. Okay, this 2, and it will be equivalent to you would have here is sigma 2. Okay, sigma 2 minus the pre-images minus a countable set. Now you might do a refinement of this partition. Okay? Like you might say, I want to look at, if I define this, so this is a half, this is a quarter, this is 3/4, this is 1. You might do a refinement of this partition. So the original partition P1 was just having elements 0, half, and a half, and 1. You might define P2, which is 0, a quarter, and a half, and 3/4, and 3/4, and 1. But this partition doesn't make this dynamical system a full branch map. This partition doesn't make this dynamics a full branch map. But if you take, so this was f. If you take f squared, which will be 4x mod 1, this guy will be a full branch map. Now both, they give rise to two different symbolic dynamics. Okay, for this one you will have a symbolic dynamics which is 0 and 1, a sequence of 0 and 1. Okay, so these are A0, A1, and so on. AI is in, okay, sorry, I should write 0, 1 to the power n. And this guy you will have sigma 4, which is 0, 1, 2, 3 to the power n. Now, a question is that you might ask whether these systems are equivalent, these two guys. If these two guys were equivalent, just a naive argument, if these two guys were equivalent, it would mean these two are equivalent. But these two are, they cannot be equivalent, these two dynamical systems, for many reasons, f and f squared. Because if two dynamical systems are equivalent, you should map periodic orbit to periodic orbit, fixed point to fixed point. And this guy, this one has more periodic orbit than this one. That's just one naive argument. So an exercise would be to prove that two symbolic cannot be equivalent if the number of symbols are different. Today I'm very, very slow. So exercise. So suppose that you have two symbolic dynamics to the power n to itself, and sigma 2 L to the power n to itself. So, and then, you have mu and nu, their corresponding Bernoulli measures, mu 1 and mu 2, the corresponding Bernoulli measures. So, show that if mu k is different from L, then sigma 1 mu 1 and sigma 2 mu 2 cannot be equivalent. Okay? Yes. I think I spent too much time on this. For this, one easy way to see how it works here is that it's a roundabout way. It's not the most direct way to see it, but just see that these two dynamics, they cannot be equivalent. Okay, let's go now to spectral, which is more interesting, I think. Spectral equivalence. That was ergodic. So yeah. So always we have our two dynamical system, F and G. So we have F mu and G nu that are given. Remember the Koopman operator. So UF, that is from L2 mu to L2 mu. It takes a function and it just takes the iteration by the dynamics. Okay? Yeah, we have seen this operator in the previous lectures when we were proving, for instance, invariant function, like Birkhoff ergodic theorems and stuff. Okay, so definition. F mu and G nu are spectrally equivalent if there exists some unitary operator L that is defined from L2 mu to L2 nu. This plays a role of the function phi that was from one space to the other. Okay, this is nu. Such that it kind of conjugates the two Koopman operators, because L composed with UF. Okay. So remember, I talked about this unitary. It just means that L star is identity. Okay. So remark or a lamb or a remark is that ergodic equivalence implies spectral equivalence. Implies spectral equivalence. Yeah, usually spectral properties are kind of weaker because you don't do something with the dynamics, you look at it in the space of functions. So usually these properties are stronger than these ones, like the spectral properties, okay? Yeah. The way to see this is, in fact, if you have ergodic equivalence, you have this map, this C. I erase it. You want just to define this operator L. That's what you want to define. In the operator L, you define it as you take L to be L of the function C is just C composed with phi, where phi is the one you get from the ergodic equivalence. So this is U C of C. So C is given by ergodic equivalence. Yeah, so yeah, you can check that U is unitary, and it conjugates the two. It conjugates the two Koopman operators. You can see that U F composed with R is composed with U G. Like if you consider two ergodic equivalence guys here. Now where L here is just this guy. But there's a warning that this way is not true in general, okay? This way is not true in general. So the reverse, the spectral equivalence does not necessarily, spectral equivalence does not necessarily implies ergodic equivalence. Okay. There is a counterexample that that one gets from the Bernoulli shift with infinite symbols. Okay, when you have this guy having infinite symbols, you can prove that there are all spectral equivalents, but they cannot be ergodic equivalents because they might have different entropies. Okay, but we don't have yet all the tools to write the details on that. Yeah, but there's a counterexample for this from using the two-sided Bernoulli shift with infinite symbols. Yeah, by the way, I forgot to say, like, what I was doing here, if you wanted to do it for the Gauss map, you can still do it, but you will have infinite symbols here. You will have infinite symbols, and that's more difficult to study, okay? Symbolic dynamics with infinite symbols is much more difficult to study, okay? That's why in some cases, people just do this correspondence when you have finitely many symbols. Yeah, and actually this is very much used also in general system, like in uniform hyperbolic systems, like what is called like Anosov systems and stuff. In the 70s, this was very much used, for instance, by Bowen to prove many properties. Like he constructed an analog of this partition, which is called a Markov partition, and you can do this correspondence, and you get all the property of your dynamics by just studying the dynamics on the shift, by just studying this guy here. Okay. Anyway, so. Today I'm very slow. Yeah, so if you have ergodic equivalence, today I'm very, very slow. Yeah, we have this, and we want to close now with what you get from spectral equivalence, like how it behaves with respect to mixing property that we see in spectral equivalence. Yeah, I define spectral equivalence without telling what the spectrum means. So let me recall that if you have a Banach space, a E Banach space, you can, in a linear and bounded operator, linear and bounded, you can define the spectrum of A. So this is over complex, okay? A complex Banach space. This guy is not injective. So this defines the spectrum of A. Now the spectrum of a dynamical system, so given F mu, the spectrum of a dynamical system F mu is the spectrum of the Koopman operator, the associated Koopman operator. Of the associated Koopman operator. UF. Yeah, so you can easily remark that if you have F mu equivalent to G nu ergodic equivalence, so this implies that they have the same spectrum, okay? The spectrum of UF is the same as the spectrum of UG. Just because you can see that UG minus lambda identity, this is because UG you can write it as L minus 1. L is what you get from ergodic equivalence composed with UF minus lambda identity times L. Yeah, this tells you that if this guy is not injective, this guy is not injective. So they have the same spectrum. Meaning UG is not injective if and only if UF is not injective. Minus identity, sorry. UF minus. Okay. And see that the constant function 1 is always in the spectrum, right? Is always in the spectrum of the Koopman operator, okay? So remark that C is identically 1 is always is always an eigenvalue, okay? An eigenvector, sorry, is always an eigenvector of UF with associated eigenvalue 1, with associated eigenvalue lambda equals 1. and see that if when f recall that if f mu is ergodic, okay, then we have seen that the only invariant function or the only invariant function are constant. So then phi composed with f, because phi implies that phi is constant almost everywhere, mu almost everywhere. We have seen this. So this tells you that ergodicity implies that the eigenvalue 1, the eigenvalue 1, which is in the spectrum of mu f, has multiplicity 1. And the corresponding eigenspace is given by a constant function, eigenvector, sorry. I mean, with this, you can see that another characterization of ergodicity is that remark so you can see that f mu is ergodic if and only if the only if only for any if g nu is, sorry, let me write it here, if only if g nu is equivalent to f nu in a spectral way, f mu. I'm very, very slow today. Okay. Yeah. So if any g, so the eigenvalue, if g nu, then the eigenvalue 1 of mu g has multiplicity 1. It's okay. So this is another characterization of ergodicity using this operator, the Koopman operator. I mean, it's not a characterization. It would be helpful if you know. It would be the way to use this remark would be if you know that this guy is ergodic in spectral equivalence to another one, you can get that one has multiplicity 1 for this system. Okay, that's one way to use it. I mean, you cannot say you are proving ergodicity using this property. There's no way to do that. Like, to prove ergodicity using this, you would check that for any such a function, one has multiplicity 1, and that's not doable. Okay. Now, so this is just to say that ergodicity is an invariant of spectral equivalence. Is an invariant of spectral equivalence. Now, how about mixing and spectral equivalence? So let's say we suppose that we have a system that is mixing. We know that in particular it is ergodic because mixing is stronger than ergodic. When I say mixing, I measure theoretic mixing. Okay, we discussed this in the previous lecture. And let's consider we are given G nu, which is spectral equivalence to F nu. F mu. Can we conclude that this guy is also mixing? Is G nu mixing? Okay. The answer is yes. Okay. To prove mixing, it's enough to. So you take two functions. So, to answer this question, it's enough to check that, to take, these are two L2 nu, and you look at this limit when n goes to infinity of the integral of C composed with Gn times C d nu. So this is what you want to prove that is converging to. This is what you want to prove that is converging to integral of C d nu, integral of C d mu. This is what you want, okay? Now see that this limit is just, this guy is just the inner product between two guys in L2, and this one is just the iteration of the Koopman operator. Okay, so this quantity here, plus Gn times C d nu, is just UGN C phi and C. This is L2, okay? The inner product. You can use the fact that the operator L is unitary, and that you use first the fact that the operator L, there's a you suppose that you have spectral equivalence. So there's an operator L that conjugate the two Koopman operator, and that operator is unitary. You can do this. You can put here L minus 1 UGN C in L minus 1. Okay, this is the inner product. This is because L is unitary by the definition of being this guy here. Now the fact that L conjugates the two Koopman operators, you can exchange these two, and what you would have here UF, okay? So you would have UF in L minus 1, see, and L minus 1, like this. And you know that the assumption is that F is mixing. So this is converging to, this guy is converging to the integral of L minus 1 C phi and d mu, the integral of L minus 1 d mu. Okay, this is because of mixing here. This is a definition of mixing, or a characterization of mixing. And now you can see that this quantity is just, you can see that this guy here, L minus 1 C d mu. So this is L minus 1 C is 1. So this is L2, the inner product. And you can use again the fact that L is unitary. You can write this as, so you put this here and you use the fact that L is conjugating the two Koopman operators. Okay. Oh no, here I should put L minus 1. Sorry. And this you can just write it as, so this is mu nu, and this is, yeah. And similarly here also. So at the end what you prove is the integral of phi composed with Gn d nu is converging. As n goes to infinity, and yeah, and this is mixing. This is mixing. Put any arbitrary guys. So mixing is also an invariant of spectral equivalence. So mixing is an invariant of spectral equivalence. Now how about weak mixing? So so how about weak mixing? Because we defined, we did, what did we do? Ergodicity, we have seen ergodicity goes through spectral equivalence, mixing goes through spectral equivalence. So how about weak mixing? There is this theorem that gives a characterization of weak mixing. So I will close that to there. Is weak mixing. So this is needed here, the fact that this guy is invertible. If and only if the constant function are the only eigenvectors of the Koopman operator. Yeah. So for this, the proof of this one way is easy. It's not difficult. Like if you have weak mixing, had proved that one is only, but the other way is more delicate. It requires some non-trivial representations of these measures and stuff. So I will not do the proof of this theorem here for the second part, this implication. If you want to follow it in the book, it's using some non-trivial representations, and there's a proof of the book, but it uses some non-trivial representations of these measures, okay, using complex analysis, which I'm not sure. So if you look at, you can see it. If you can follow the second part of the proof, it's fine. If you cannot follow it, you can check the results using in the appendix. And it would be also a good, presentation to present a complete proof of this theorem in the more general setting, to present it at the end of this course also. This would be something good. So basically this is what I wanted to say in this chapter. This is just a short chapter that just tells you that when you have equivalent system, what you get, like what are the properties you get. Because for the next part, I want to move to the chapter about entropy, which is very interesting and central in this course, like the definition of entropy, the measure, theoretic entropy, and topological entropy. So that's what we will start on Friday. We will start the chapter on entropy. Yeah, and then we will see. So for today, I will stop here.